Let's talk about the gradient of a scalar field. Now, just a reminder about scalar and vector field. If you say you are in a room, all right, and you have temperature, you know that temperature is a scalar product. You have a thermometer measuring the temperature, right, of the room. Let me just put hidden details for the corners here. All right. So you measure the temperature here, 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 at different points inside the room. Now I could keep adding more and more dots to show the various points where temperature exists, but that would require an infinite number of dots, right? Now, what you have there, temperature being a scalar, and various points where you measure the temperature, is called a scalar field, right? Now, you can measure the temperature from place to place, and if you have an air conditioning unit right here, an AC unit there, it's cooler near to the AC unit, right? Now, you have different temperatures throughout the room. The further you go away from it, the warmer the temperature is, right? Now, you might measure temperature here and measure another temperature here. So draw a line between them. Now, that length of the line represents the difference in temperature. And the direction, let's put an arrow here, it tells you the rate of increase of temperature, right? Now, the gradient of the temperature, that temperature field, it is a vector because it has magnitude and direction. You have the magnitude, which is the difference in temperature, and the direction from warmest to coldest within that region. So the gradient of the temperature field, it tells you the direction of the greatest increase of temperature. All right? So here, what happened? The gradient, sometimes called the grad, right? And it's represented by the upside down triangle. Now the grad, the gradient, you know that when you talk about gradient, it has to do something, it has something to do with differentiation, right? Because when you differentiate a function, what you're doing is finding the gradient vector. So it is the partial derivative of something with respect to x, change in x. So you have your x-axis, your y-axis, and your z-axis. So the x-axis is going to your lower right, y-axis to your left, and the z-axis upwards. in the direction of x, right, you are looking at the the rate of change of some function, right? Call it f, the rate of change of it with respect to x. And when you're changing x, you're going in the I direction, plus the partial derivative of f with respect to y, that means the rate at which the function is changing as you go in the y direction, and as you change y, and it will be in the direction j, same as change going along the y-axis, plus the partial derivative of a function with respect to z along the z-axis, means you're going in the k direction. Alright? So what you have there is the gradient of a vector function. Now, what it does, grad f works on a scalar field to yield a vector. Because remember, the scalar field here was in temperature, but the gradient shows you the magnitude, the difference between the highest and lowest, and the direction at which that change is occurring, the greatest rate of change of temperature, magnitude and direction of the greatest rate of change of temperature. So it works on a scalar, right? The gradient works on a scalar, not on a vector. So f is not going to be some value of xi plus some value of yj plus some value of zk. This itself is a vector. You cannot really find the gradient of a vector. It must be a scalar, alright? So it's going to be some ax to the n, y to the n, z, alright, n, m, o, if you consider those numbers as powers, right? It may be a case where you have 5x squared plus 3x y squared z cube or something like that, right? You don't have any I, j and k in it, because I, j and k would be directions. This itself is a scalar, so you can find the gradient of the scalar, of this scalar, right? Now, that is an example of a scalar function where you can find the gradient of this scalar function. Now, in a future video in this playlist, we're going to find the gradient, the divergence, which we'll look at later on, and then the curl, which we'll look at later on. And then we do some examples. So this is a function of x, y, and z. Alright? No I, j, or k in it. It must be a scalar. So the grad, and you would have seen this before when we were doing directional derivatives, right? in previous videos. The grad, the gradient or the grad of a function, scalar function, will yield this vector function. Right? Okay, so in the next videos, we talk about what is called the divergence and the curl. So I'll see you in the next videos then.